Quality Control Improvement, Module 2, Lecture 3. Let's take a look at some examples using the various distributions. The learning objective for Lecture 3 is to select the appropriate probability distribution for use in specific applications. Reading assignment is Chapter 3, pages 65 through 96. So in the first example, let's take a look at a fictitious company called Greer Aircraft Engine, which sells aircraft engines to commercial airlines. Greer is offering a new performance-based sales contract in which Greer will guarantee that its engines will provide a certain amount of lifetime flight hours, subject to the airline purchasing a preventive maintenance service plan that is also provided by Greer, of course. Greer believes that this performance-based contract will lead to additional sales as well as additional income from providing the associated preventive maintenance and servicing. From extensive flight testing and computer simulations, Greer's engineering group has estimated that if their engines receive proper parts and replacement, and of course preventive maintenance, the mean lifetime flight hours achieved is normally distributed with a mean of 36,500 hours and a standard deviation of 5,000 hours. So this first part is critical. You have to establish through testing what the mean is and what the standard deviation so you can make predictions. Now what Greer is interested in, they would like to know what percentage of its aircraft engines will be expected to last more than 40,000 hours. In other words, what's the probability that an aircraft engine flight hours X will exceed 40,000? So here we're going to set X as our variable for lifetime of the engines. So in this problem, the failure of the engines will be normally distributed with a given mean and standard deviation, which we're told in the problem. So the answer to our problem can be found by finding the area under the curve to the right of 40,000, because that's what we're interested in. So here's your standard normal distribution. It has a standard deviation of 5,000 and a mean of 36,500. So I've marked 40,000, and so what we're interested in is the percentage of engines that are in the right tail. What's the probability that X, which is our engine lifetime, is greater than or equal to 40,000? So let's use Minitab to calculate this since it's so handy. From Minitab, go to Graph, Probability Distribution, Plot, View Probability. So here you kind of have to be careful because there's one called Probability Plot, but you actually want the one that's called Probability Distribution Plot. So when you click on this, it will pull up this little side shot here. We want to select View Probability because that's what we're interested in. We're actually going to calculate things, so we need this View Probability option. So click on this and click OK. So for our particular situation, you can select the distribution. If you click this, hold it down, select normal. I think normal is the default, but you want to make sure this is set to normal. You want to enter the mean and the standard deviation from the problem and click OK. Now click on shaded area, and you want to click on the X value and click on right tail because that's what we're interested in. So so this gives you different options. If you were interested in the left tail or both tails or in the middle, you select that one appropriately. The X value we're going to actually enter. We're told that we're interested in the X value of 40,000. We want to find the probability that X, which is the lifetime, is greater than 40,000. So click on the X value and type in 40,000 and click OK. So Minitab will generate the plot shown here to the right. You can see the right tail has been highlighted. So you can see 40,000, you can see the mean, you can see the shaded area as the area we're interested in. This is the percentage of engines that probability for being greater than 40,000. It's shown as 0.2420. So that's our probability. So we can conclude that about 24.2% of aircraft engines will exceed the 40,000 lifetime flight hours. So let's now, for example, let's now assume that Greer is considering a guarantee that will provide a discount on a replacement engine aircraft if the original engine does not meet the lifetime flight hour guarantee. So what they're, so they're trying to figure this out. So they need to know, they don't want to pay back too much. They don't want to lose too much money in this. So what they're, how many lifetime flight hours should guarantee if Greer wants no more than 10% of aircraft engines to be eligible for the discount guarantee? So this is real critical in determining how not to lose money. You want to provide a sort of a guarantee, but if you have 90% of these engines have to be replaced, well, that's going to cost a lot of money. So you want to figure this out. You want to figure out how many lifetime hours if it wants no more than 10%. So the solution here is illustrated graphically below. So in this case, we're actually dealing with the left end tail. So we still have the same normal distribution. It still has the same mean and same standard deviation. So here we want the number of that fall in this left tail to be no more than 10% of the engines that are eligible for this discount. So here we do sort of the same thing, except we select the left tail. So in this case, let's go to Calc, Probability Distributions, and select Normal, and you should get this window pop up. In this case, we want to select Inverse Cumulative Probability. We type in our mean, type in our standard deviation, type in our input constant, 0.1. So this is our 10%. We then click OK. So Minitab will solve this problem. It'll produce the X value that gives you 10%. That's why it's sort of an inverse cumulative probability. So we get the answer of roughly 30,000 hours. It's a little bit more than that, 30,092.2 hours. So that's our flight hours. So using this information, though, maybe Greer team would probably round this off, and select, well, if we suggest a lifetime flight hour guarantee of 30,000 hours, that'll guarantee that no more of these are more than 10%. So that shows a very useful application, a very practical application of the normal distribution. Now let's look at example 3. Let's go back to the Greer example. Maybe Greer is also interested in knowing the probability that an engine will have a lifetime flight hours greater than 30,000, but less than 40,000. 30,000, we sort of determine that value. We want to, so let's, how many engines are going to fall? What's the probability of the engine doing this? So here, again, go to Minitab, select Normal, type in our mean and our standard deviation, like before. Here we want to enter the X value. So you click on shaded area, click on middle, select the X value and type in the lower and upper X values. Then click OK. So when you do that, Minitab will generate the following plot. So here it produces the plot, produces the probability of 0.6612. So therefore, the probability that the lifetime flight hours for an aircraft engine will be between 30,000 and 40,000 hours is 0.6612, or roughly 66%. Example 4, let's take a look at business startup companies. So let's say in this particular example that 80% of all business startups in the IT industry report that they generate a profit in their first year. If a sample of 10 new IT business startups is selected, find the probability that exactly 7 will generate a profit in their first year. So the first thing we need to determine is which probability model we need. So let's summarize the data. There are only 2 possible mutually exclusive outcomes. Either you generate a profit in the first year or you do not. There are also a fixed number of trials or startups. There's 10 in this case. The IT startups are independent. We're going to assume that one company is totally independent of another company. One guy doesn't own both of them, for example. And so in this example, this is reasonable to assume that this is true. The probability of success for each startup is 0.8. So based on these initial conditions of the problem, Here, the binomial distribution is needed. So go back and look at the binomial distribution if you have a hard time seeing exactly why we're going to select, why this model fits the binomial distribution. So let's use Minitab to solve this. So we open Minitab, we enter data in the first column. The first row, I call this trials. That's optional. You don't really have to call it anything. You can leave it blank. And I listed 0 through 10. So for Minitab, go to Calc, Probability Distributions, and select Binomial, since that's what we need in this case. When you do that, it'll open up the following window. Make sure probability is selected. Enter the number of trials, which is 10. The event probability is 0.8. Input column is C1. Typically this will be empty, and so you'll have to click in this area here, click on C1 and then hit select and it'll fill it in. I think you can also just type in C1. But once you get it looking like this, click OK. So here Minitab provides a worksheet which will gives us the answer. So it says binomial with n equals 10 and the probability is 0.8. So what it did is it took our column of x's and it calculated what the probabilities are and filled them in. So the one we're interested in is 7. So here, when the probability when x is equal to 7 is 0.2013. So what does that mean? That means that there's a 20.13% probability that exactly 7 of 10 IT startups will generate a profit in their first year, when the probability of a profit in the first year for each startup is 80%. You can see it gives you all the data. So if you're interested in 8 or 9, you can actually see, and the most likely outcome is 8, right, based on the data. As our last example, let's look at patients arriving at a hospital. Suppose we're interested in the number of patients who arrive at the emergency room of a large hospital during a 15-minute period on weekday mornings. Suppose that the average number of patients arriving during a 15-minute time period is 10. The hospital management's team wants to know the probability of exactly 5 arrivals in 15 minutes. So here you can see, in order to use all these distributions, you have to have some input data. Also, so now we need to figure out which distribution do we use. That's the hard part. So first, let's summarize the data. Here we have a certain number of events occurring during a fixed time interval, and that's critical. These events are known to occur independently with a constant mean rate. In other words, there's not, one patient is arriving is not depending on another patient arriving. So here, based on these conditions, the Poisson distribution is what is needed. Often that's what you have when you have a certain number of events during a fixed time interval. So to calculate this, from Minitab, let's go to Calc, Probability Distribution, and choose Poisson. So here we enter the data that we're given. The mean is 10. The input constant is 5. Click OK, and then Minitab will give you the results. So it performs that exactly 5 arriving is going to be 0.0378, so roughly 3.8% is the probability. So no, it's not very likely in this case. Okay, so I hope these examples help you. The web is full of examples of using the normal binomial and Poisson distributions. So if you find other lectures out there that help clarify the information or provide you more examples, then certainly go forth and try to find those out. I think the critical thing is trying to figure out exactly what distribution you need for a specific situation.